Let me share my screen. Okay, share entire screen. Let me know if you can see my screen. Can you see my screen?
Yep.
All right. Okay. So yeah, thanks everybody for coming today. So yeah, today we will talk about hash-based multi-signature signatures for post-quantum Ethereum. My name is Philip. I'm located in Germany. I'm a software engineer turned cryptography engineer, so I love cryptography. These are my socials. You can always reach out if you have any questions. And yeah, this is my blog where I also post some posts about cryptography. So without any further ado, let's jump straight into it. So I just want to highlight the goals for this talk of today. So the goals are that we quickly do a quick recap on hash-based one-time signature schemes. Then I will explain how hash-based multi-signature schemes work. Then I want to show how hash-based multi-signatures will be used in the Beam chain. This is like, we still don't know if it will be used that way, but it's kind of like a candidate construction. That's why there's this asterisk there. And then we'll talk about the trade-offs of hash-based multi-signature schemes and also the parameter selection for the implementation later on in the Beam chain if we do so. So this is the kind of like a continuation of a presentation series, if you will. So there was already a first presentation on hash-based signatures, which was called Hash-Based Signatures from First Principles. Later on, I will share this presentation, and you can just click on this link, and then you will be redirected to the first presentation. In the first presentation, we talked about hash-based signatures in general. I wrote on Telegram that it might be useful to go over this, but it's definitely not a prerequisite because this presentation is also self-contained. So even if you don't have any background in hash-based signatures, you should be able to follow along. Okay, and then there is this paper that was published in mid-January this year by the Ethereum Foundation, which has the same title as the presentation, or it's rather the other way around. So I choose the same title, which is also hash-based multi-signatures for post-quantum Ethereum. And this paper is like, I think 50 pages or something like that. It goes into the nitty-gritty details of all of this. The presentation I do today is a little bit more high level, but once you, or if you follow along, you should also be able to dive deeper into the paper and understand what's going on. If you look at the proofs, for example, there's a lot of proofs in there, and yeah, and things like that. Okay, so the question we should answer first before we go into the presentation and into the proposal that is being made here is, why do we even need this in the first place? And the answer to this is, right now BLS signatures are used in Ethereum's POS consensus, and they are based on elliptic curve cryptography. And elliptic curve cryptography, unfortunately, isn't post-quantum secure as we know. Or yeah, there's like some, in the media, there is some kind of like, some kind of, you can find in the news a lot about like post-quantum cryptography now being rolled out because there's this quantum thread. You might have heard about Willow, which is like Google's latest research advancement when it comes to post-quantum algorithms and constructions and things like that. So it's definitely worthwhile to switch from elliptic curve cryptography to something that is post-quantum secure. Okay, so the current state, this is roughly like a very high level how it currently works in Ethereum's POS consensus. So there is like a block being produced, then validators sign the block via BLS, and then the aggregators which are aggregating the signatures with a BLS signature aggregation scheme, right? So what you do is you have like multiple signatures being generated for the block, and then you kind of like compress. You don't really compress, you aggregate them, but you have just one very small signature, and then you just need to have all the public keys. You can then also combine, and then you can verify that either all the signatures are valid, and if just one signature is invalid, the whole verification of the whole aggregated signature is invalid. So it's a very interesting scheme. and also a very efficient one, but unfortunately not post-quantum secure. So the desired state is that we once again produce a block, and then we sign the block with a post-quantum signature scheme, and then we aggregate all the signatures with a post-quantum snark. So a succinct non-interactive argument of knowledge. And the idea here is that you can think about it that you kind of like say, hey, I saw these signatures. So I generate like a proof that I saw these signatures being generated for the block. That's the post-quantum snark bit. So there's the signing, which is post-quantum, and then there's also the aggregation, which should also be post-quantum. And if you use something like Groth 16 or something that uses elliptic curve cryptography for the snark, then you end up in the first place, right? You end up where you started at, because then you reintroduce the post-quantum thread. That's why you also need a post-quantum snark. Should totally make sense, I think. Okay, now with that context, we can do a quick recap on the Winternitz one-time signature scheme. And before doing so, we just briefly recap what cryptographic hash functions are all about. They have certain properties. This is just a very condensed write-up or list. So there are, of course, more interesting properties of hash functions, but these are the ones we care about. So any output of H looks completely random. So if you put something in there, you cannot predict what will be the output of the hash function. Then H maps an arbitrary length input to a fixed length output. So you can put a whole DVD into the hash function, like all the binary data of a DVD, but you still get a fixed length output back. And then any M always maps to the same H. So if you put a message M into the hash function as an input, you always get back the same output. So if you have hello world, you always get the same H back. But if you just flip one bit, if you just hello, comma, world, you get a completely different H back. But it will always map to the same output. And given M, it's easy to compute H. It's very efficient, if you will. So yeah, you put an M in, it's very fast and efficient to get the output H. But if you have H only, it's very hard or computationally infeasible to go back to M, right? So this is kind of like denoted here. So you have the hash function, you put M in, you get the digest. It's usually also sometimes called back. And then if you have H, it's very hard to reverse what M actually was. Okay, I think, yeah, if you're familiar with hash functions, this shouldn't be anything surprising. But with that, what we can do, and this is kind of like the interesting thing with Winternitz's signature scheme, is we can create hash chains. So the idea is basically you start with a message M, and then you hash it, and M can be of any length, but the output will be of a fixed length. And then you take this output of the first hash function call, and then you hash it again, and then you hash it again, and again, and again, and so on. And I denote this with an I here. So you have I hash iterations you can do, where you just call the hash function over and over again of the output of the previous hash function application. And this here just shows you that if you have I, you can compute I plus 1, because you can just hash the output of H of I again, and then you have I plus 1. So you go one step further in the hash chain. And the cool thing is, if you have this hash chain construction, what you can do is you can say, you know what, we have a secret key, so we just randomly sample a 256-bit value, for example. Then we hash it, let's say, 10 times. And then we say, once we hash it 10 times, we have a final hash digest. And this is then our public key. So, you know, we can basically hash the secret we put in 10 times, and then we have a public key. And this way you already have some kind of key generation, if you think about it. Now the question is, now what? Yeah, what should I do with this? How should I even sign something with this? And this is the big idea behind Winternitz OTS. So if you get an interim value at position I, and you know the overall length of the hash chain, then you can use the pending like iterations you can figure out until you should reach PK, right? Because if you know the length of the chain, if you know here, for example, that this person hashed the secret key over and over again 10 times, then you know if you're at position 5, you have to hash 5 times again, and if you end up with PK, then the signature should be valid. So this is the big idea. And this is what I've called in the previous presentation the simple Winternitz one-time signature scheme. And yeah, it works like this. We can go over this once again real quick. So you generate a private key SK by randomly sampling some bits. Then you pick a hash function that produces an output of length n bits. And then you hash the private key 2 to the power of n minus 1 times to generate the public key. And this 2 to the power of n, if you are familiar with computer science terms, this is because it's binary. Because in signing, what we do is we have our message m. We hash it so that we get a fixed digest size. Right? We also are using a hash function. We just use it to condense the length of the input. And then we interpret this as a number. So you can always interpret this, for example, as a 256-bit number, and which goes from 0 to
you froze.
Did we lose Philip?
Yeah, I think his network's down.
Sorry, I think I dropped. Let me try again. I'm not sharing, right? So let me try again. You can maybe tell me where the connection was lost.
Very recently, only maybe 10 words ago.
Ah, okay. So let me rewind 10 words then. Cool, yeah. So what you can do is, in the verification, we are now, essentially, we generate our signature, we hash it let's say 10 times. Now we need to figure out how many times do we need to hash the value over and over again until we reach a public key. And we can just compute this as this 2 to the power of n minus 1 minus the x value here. And then we just hash the signature. We have j times, which is like this here, right? J times, and then we check, do we end up with the public key value? And then if we do, then the signature is valid. So this is an image of this. We have our secret key here. In key generation, we start with a secret key, and then we hash all the way to the public key value here. And then if we, for example, have the message M4, we hash the secret key 4 times here. So we end up with our signature here. So this is the signing step. And then the person who is verifying, they just need to know how long the hash chain is in total, and then they can figure out this J value we saw. And then they can just hash the signature over and over again here until they should reach PK. And if they do, they know the signature is valid. So this is the main idea behind the Winternitz one-time signature scheme. It's very elegant, only uses hash functions, but there are some problems with this. And there are 2 major problems. It's very computationally expensive, because hashing is a sequential operations. You cannot easily parallelize it, if you can parallelize it at all. And then you might have to do a lot of hash computation. So for example, if this is 2 to the power of 256, you first of all have to go all the way to compute the public key, which is a bunch of computations you have to do. It might even be computationally infeasible. And then even if you you have some value in between here, you still have to compute hash operations, like multiple ones in succession to reach the public key. So it's a little bit computationally expensive. And there are also signature forgeries possible, because we can always go one step further here, right? We can always go in this direction, because if we just apply a hash function here again, we end up here. So we can very easily forge a signature by just taking an existing one and then hashing it again to get a new signature in the hash chain here. Okay. And the computationally expensive part is very easy to fix. It's your typical divide and conquer approach. So what you do is the message you have, you split into L chunks of W bits each. And then you have one chain for each chunk that you have generated that has a maximum length of 2 to the power of W. And then each hash chain has a dedicated private key and a dedicated public key. And then the signing and verifying is done per hash chain. Now, this is very like a mathematical way to express it. I also have a picture for you here. So you have your message here. You split it up into the chunks. So these are the message chunks. So you have W bits of for every message chunk, and then you have L chunks. So as an example, you have like a message that has 4 bits. What you can do is you can split up into 2 bits each. So you have like 2 chunks of 2 bits, and one chunk can or one of these chain can then represent 0, 0, 0, 1, 1, 0, 1, 1, and the other one as well. And that way you can then have 2 chains only, and then you can kind of like split up the work. And then for every chain, as we saw, we have to generate an own secret key here, and then we also will generate a public key for every chain. And yeah, depending on the parameters W and L, we might have more chains which are like smaller in the overall like length here, or we might have very long chains but only a few of them. There is this problem. If you look at this, it's a little bit annoying, right? You have to distribute all the public keys, because in verification you do this per chain. So what the person needs to do is they need to get the signature for every chain here, and then they need to compute the hash function over and over again, and then compare this to the individual public keys. So they need to get the public keys in the first place so that they can do the verification, which is annoying, because if you have a lot of chains, there are a lot of public keys to publish. And the solution is very simple. You might have guessed it already. You just hash all the public keys. So you apply a hash function to the public keys to hash it into one single public key, and this is depicted here. So you have the public keys, you hash all of them, and then you end up with one public key you can share. And then it doesn't really matter how many chains you have, because you always have just one public key. So in verification, there's a minor change we will now talk about. So it's the same thing. You split the message into L chunks of W bits each, as we have seen. Then you have one hash chain for each chunk that has max length 2 to the power of W, and then you have a dedicated private key, a dedicated public key for every chain. Then you hash all the public keys, PKI, into this one like derived public key. So you only have one public key to distribute. Then signing and verifying is still done per hash chain, but during the verification, you just combine all the public keys you get, and then you hash them, and then you see like, oh, do I end up at this public key that was shared with me previously? And if so, the signature is valid. So this is, you can see like in bold here, the changes we just have to do. And then we already solved this problem of distributing a lot of public keys, which is annoying. Now, the second thing is signature forgeries. As we have seen, if you have a hash, or if you have a signature which is like in the middle of the chain, then you can always apply the hash function again to get a new signature, sigma prime, which is also valid. And what we can do is we can compute a checksum and just append it to the data that will be signed, and then the checksum changes whenever any of the sigma i's, so the individual signatures we generate per chain, is changed. And this is the formula for the checksum computation. The general idea is that this is just the sum of the missing iterations, the hash iterations you need to do to get to the public key part. And I also have a picture. This is a mathematical representation here. I also have a picture. I can show in a minute that should make this more clear how the checksum computation works. But the general idea is that this C, because it's like the pending, the sum of the pending iterations you have to apply. And if we go one step further in the chain, so if we forge a signature, the checksum will be reduced and by 1. And the checksum is also hashed with a dedicated secret key. And if we reduce it by 1, we would need in the checksum, we would need to go back, which we cannot do because hash functions are always they don't allow you to, as we saw from, if you have an H, you cannot go back to the M. So you cannot undo a hash operations. You can only move forward. So this is why it works. And now I can show you the picture. So now it should be much, much easier to understand. So here we have the number of pending hash operations we have to apply. This is like 1 here. Here we have to do 2. Here we have to do none because we are already there. And then if we just add them together, we have 3. So 1 plus 2 here. And this is our checksum. And then the checksum is also then signed here with a dedicated checksum private key. And then if we now, for example, move forward somewhere in here, if we want to forge a signature for a message M prime, as you can see here, we move forward here. But then we only have 2, so we would need to undo 1 hash operation here, but we cannot do this because hash functions are always one way, right? You cannot undo a hash operation. You can only move forward, and that's why this checksum trick works. I can show it again. You can see it here. We were here. It's like 3. And now if we want to forge a signature here by moving forward here, we would need to undo 1 here because it's now only 2 operations pending. So we need to go to here, which we cannot do because we would have to undo 1 operation here. So this is cool, and this is the classical Winternitz one-time signature scheme we just saw. It's this idea of splitting things up into multiple chains and with a different like bit size W, and then you have the checksum you add to it so that signatures cannot be forged. But checksums are also a little bit inefficient if you think about it, because they add an additional overhead. Because if we look here, we have like a message with 3 chunks, but then we always have to carry out this checksum computation here all the time during like signature generation, also verification. So there's like this additional overhead we have to add, which adds to the overall signature size. And the cool thing is that there is an idea where you can get rid of the checksum. And the idea is a target sum. So you define this target sum, and you only allow messages that result in the predefined sum of interim values. I will also show a picture in a minute, which should make this more clear. But the idea is that you compute this target sum, which should be the number of hash chains times the overall length of a hash chain divided by 2 roughly. And then with a little bit of trial and error, you can configure those parameters W and L so that you can fit all the messages you want to sign into this so that it's compliant with this target sum. And here's a picture which makes this hopefully a little bit more clear how this works. And the idea here is we have a message. We have 4 message chunks here. So we don't have this signature, this checksum part here. We already got rid of this. And the target sum here, for example, we say it's 9. And 9 is, for example, here you can see we apply 2 hash operations here. So it's 2 plus 3 plus 3 plus 1. So it's 9. So this message here would be compliant with the target sum goal of roughly 9. And then if you want to forge a signature, you have to find some other combination here that's also equal to 9. And if you then, for example, want to move forward here in this hash chain on 1 value here, you would then have to go back on another place here. So what we do here is we swap these values, because if we swap them, they are also equal to 9, so they are also compliant with this target sum requirement. But the problem is we now have to go back 1 iteration here, for example, to have another valid signature. And this once again requires you to go back and undo 1 hash computation, which isn't possible, right? So this is the target sum idea. And this is target sum Winternitz OTS. So it's kind of like getting rid of the checksum and using this target sum we saw to almost like, it's not like a different way of computing a checksum, but it makes sure that if you get a signature, that you can then check, is this compliant with the target sum, and if not, you can reject it. And also, if you want to forge a signature, you always have to be in this target sum environment. You have to make a target sum compliant, and this is, as we saw, hard to do because you might have to undo a hash operation. Okay, so these are the two Winternitz OTS schemes that are also being discussed in the paper, which is the classical Winternitz with the checksum and then the target sum Winternitz we just saw. And now the question is, we have a one-time signature scheme. How do we go from one time to many time, right? So the thing is, with Winternitz, you can only do one signature computation, and then you have to regenerate a private public key pair. If you reuse your secret key to generate a second signature, then signatures can be essentially forged. So the question now is, why is Winternitz even a one-time signature scheme? And this is very easy to see. So let's say we have a message M1 here, and we have the message is only comprised of two chunks here, so two individual hash chains. And we use SK0 and SK1, and then PK0, PK1, which result in PK. And then we compute a signature for example, for the this message 1 here, which is just one hash iteration of every secret key. And then we decide to reuse our secret and public keys. So we reuse them here, and we computed second signature. And in this case, we hash the secret key twice. So these are the signatures we publish. We think we are good because, why not reuse our secret and public keys if we already generated them? But the thing is, once you have these this information here, what you can then do is, and this should be easy to see, you can then pick some of the hash chains here and then just combine them, recombine them. So for example, as you can see here, this is also then valid. So what we did here is we kept this here in place, but we then took this second hash chain and just replaced it, replaced this one with the second hash chain, and we can do it also the other way around. So these two messages are now also valid because by reusing the secret key, we revealed parts of the secret key, if you will. So these are also valid signatures. So that's why you cannot or should not reuse your secret keys. It's only a one-time signature scheme. And now the question with this is like, okay, so how do we go from a one-time signature scheme to many-time signature schemes? And the solution, as you might have guessed already, is Merkle trees. And Merkle trees are great because they also use hash functions. So we don't introduce a new cryptographic primitive here. We are still in the hash function world, right? We apply this trick of combining multiple public keys into one using hash function. We use hash function for signature generation, key generation, and so on. And now we also can use the Merkle tree, which is also just a tree of hashes. And this also uses hash functions. So what we now do is we instantiate Winternitz OTS n times. So however often we want to sign, if we want to generate n signatures, we just instantiate Winternitz OTS n times. And then all the public keys of every individual instantiation, the big one at the top you saw, is then just a leaf of the Merkle tree. And then we can just compute a Merkle tree, and the root of the Merkle tree is our stable, if you will, stable public key. We just publish once, and then this is how it looks, right? So this is just what we saw before. Here's the public key. This is just the leaf of the Merkle tree. And then this is our long-term public key for our n signatures we can generate here. And, signing and verifying is pretty simple. You might have guessed already how it works, right? It's basically computing the signature here and then combining this with a Merkle path. And then you just submit the signature you have generated here plus the Merkle path. And then the verifier, or the person who wants to verify it, they can take these values and then check if they end up at the tree, at the root of the tree. And if they do so, then they know the signature is valid. And this is true for all the entries here in the Merkle tree. So no matter what leaf you choose here, you can always just generate the signature and provide the Merkle path, and then they can check if they end up at PK. And the good thing is also that if you use this over and over again, this Merkle tree, you can also do some kind of clever caching, so that you don't need to recompute the whole tree. For example, you can, while doing the verification, you can also cache certain leaves in the tree and make this very efficient. And this is the extended Merkle signature scheme, so XMSS. So if you Google for XMSS, this is roughly what it is. So you have a high-level idea of what the extended Merkle signature scheme is. It's used a lot. It's used in Sphinx Plus, for example, which is a NIST recommendation for a hash-based signature scheme. And it's pretty cool, I think. Now, the question is, how do we know which leaf in the tree we should choose, right? We can choose any kind of leaf. So how do we know which leaf was already chosen? Because again, you shouldn't reuse a key pair. This is also true for a leaf. You shouldn't reuse, of course, a leaf. And the question is, what leaf then, should I choose to generate my signature? And there are different ways to do this. For example, if you, Sphinx Plus has some more clever tricks to it, but one way of thinking about this is you just generate this gigantic Merkle tree, and then you just pick one at random. And if the Merkle tree is big enough, the probability of picking a leaf again is very low. And there are some things like hyper Merkle trees and so on. I won't go into the details here. This is one way of doing this. You just have a gigantic tree. There are efficient ways to compute it. You just pick one at random, one leaf. But there's a simpler case we can take advantage of in the Ethereum consensus. And I will talk about that in a second. But what we can do is we can just enumerate all the leaves from left to right. And then we can say, if we have this, we can say this is leaf number 1, this is leaf number 2, and so on until we have leaf number n. And then if we are in sync with each other, we can just say, and now we use leaf number 2 for signature generation, and now the next one, and so on. We just have to keep some kind of state to keep the tree, like the view on the tree, in sync. And this is cool because in Ethereum's consensus, what we can do is we can just assign one leaf per slot. So we can just say slot 0 has the leftmost Merkle tree leaf, and then we say slot 1 is the one next to it, right? It's like the one at position 1, and so on. And this way, even if you join, I don't know, like years later, you can always basically participate in consensus, because it's kind of like in sync because of the slots. We are the definition of a slot, and we know which slot is currently being a signature being produced for, and therefore we know which leaf to pick. And this is then the same picture we saw again a few slides ago. This is just, slot number 1 is like the leftmost Merkle tree leaf. Slot number 2 is the second Merkle tree leaf. And that way we can use the slot mechanism to stay in sync and have a shared view on the Merkle tree, which is pretty cool, I think. Okay, now the question is, we have that solved. So we solved the signature generation, right? We have now a post-quantum scheme. We can generate multiple signatures by having this Merkle tree construction sitting on top of it. But now the thing is, okay, we have this, but how do we do this aggregation part? Because in the beginning of the talk, you might remember that we briefly talked about this snark, the post-quantum snark we want to use for signature aggregation. And the thing is, this is still a little bit TBD right now. So this is here from the paper, section 3.4. We know that we want to use a post-quantum snark, but the argument here is that right now it's kind of like treated as a black box. So we assume there is one. Ideally, it's also using some kind of hash function behind the scenes, as we talked about, so that it doesn't introduce this elliptic curve cryptography primitive again, which is not post-quantum secure. But right now it's mostly treated as a black box, and this is like a next step that needs to be researched more to figure out what kind of post-quantum snark we use. But we will use for aggregation a snark. which is this idea of, oh, I saw this signature and this one too, and here's my proof that I saw it and it's correct, and so on. So yeah, this is TBD still. And then you might also think, okay, but what kind of hash functions should we actually use here? And in the paper, the proposal is to use SHA-3, which is a more conservative choice. So Ketchak, what we are currently using in Ethereum, is in fact kind of SHA-3. SHA-3 is just the parameters were a little bit tweaked, and there was this requirement of changing things a little bit during standardization. And I think Ethereum also chose Ketchak because this parameter tweaking was a little bit suspicious. I'm not totally sure about this, but SHA-3 is kind of like Ketchak, but the standardized version of Ketchak. And this is the more conservative choice because there's a lot of cryptanalysis on this already. And yeah, it's very much battle tested. And then the second one is Poseidon, and yeah, Poseidon 2 for faster aggregations. Poseidon is a ZK-friendly hash function. So if we do aggregation, for example, it's much more efficient to use Poseidon if we want to, but it's also a little bit more recent. And in fact, there is this new initiative also by the EF that will look more into Poseidon and whether it's cryptographically secure. And yeah, the other thing is, okay, now we know which hash function to use, or which hash functions are proposals for being used in the Beam chain. But we still have this this problem. There's this trade-off we have to figure out, like what the signature size versus the computation cost. Because if you have a very big signature, then the computation cost might be lower to finalize the steps to figure out if the hash function is if the signature is valid. And yeah, this is this trade-off you have to balance. And this is also discussed in the paper. So the larger the signatures, the more bandwidth is required, because if you have like a, 5 kilobyte signature and you send them around for aggregation, then you need to have a lot of bandwidth. And this is harming kind of like the decentralization, because there's like this bandwidth requirement you need to have to participate in consensus. And then for computation, if you have a lot of computation to do, so if the signature size might be smaller, but you need to do more computation, then the verification aggregation costs might go up, because then in the SNAR computation, you might need to spend more time on hashing, which is then slower, for example. So these are the two things we have to balance. And in the paper, there is the parameter selection section. There are two different tables, and I will go briefly over one table here, and you can look into the paper. It's almost at the end of the paper, where they talk about SHA-3 here, and then there's also a second table for Poseidon. I will just show you SHA-3 here. And what we talked about, we can see in the data. So this is the benchmark. So what you can see here, W is the traditional Winternitz with the checksum, if I remember correctly, and TSW is the target sum Winternitz. And this delta for the target sum means if there's like a 10, for example, this here means we kind of like do the exact target sum, and this here means we have a 10% deviation from the target sum, so that way we can have a little bit more like wiggle room for the computation. And I can show you here, we can focus on this here, and then later on we can also talk about the specific parameter selection here, what might be actually used in the Beam chain. But with the typical Winternitz, what we can already see is that the signature size goes down the longer the chain is. So this W means here, W1, for example, means you have 2 elements in the chain. And if you have only 2 elements in the chain, then you need usually more chains, which means the signature size is larger. And the longer the chain, the smaller the signature size. However, if you then take a look at the hash computations you have to do, then you have to do more computations, which is like, you can see it here in the data, right? So this average is worst case, and also the signing time and also the verifying time goes up or down respectively. And the other thing we can also see in this data here is if we compare this traditional Winternitz one with the checksum, with the target sum one, we can also see in the data that the signature size is bigger. So for example, with W here, with the bits of 1, you can see that the signature has a size of 4.17 kilobits. And with the target sum, it's slightly smaller because we have this target sum, which is kind of like this checksum replacement here. Yeah, and if you look through the data, there are definitely some interesting parameter choices here. So for example, the bit length of 4, for example, looks cool, looks very good here. But we always have to, in terms of this trade-off, we always have to think about that. Like, do we want to spend more bandwidth to send signatures around, or do we want to make it efficient so that aggregation later on is more efficient and doesn't take too long? And then the lifetime here, by the way, on the side here, what the lifetime means is how long until you need to regenerate this whole Merkle tree again. So how many signatures you can compute. And in the paper, there's one here for SHA-3, one table, and then there's another one for Poseidon. And I encourage you to look into the paper. With this background knowledge, you should roughly understand what this table is all about and what you can maybe derive like some insights from this.
Oops, we lost him again. Hey, Philip.
His mouse is still moving.
Yeah. We can't seem to hear you, Philip.
Dropping again. It's a little bit spotty today, the internet. Anyways, there are other resources. I'm not sharing my screen now because this was the last slide anyways. But this is list with additional resources you can dive into. And this Explore Expander Bootcamp presentation, there's one of the co-authors of this paper also explaining things in more depth. So if you're interested in that, you can also watch that presentation, which was very recent. So yeah, thanks again for joining. And yeah, this is how eventually, or maybe, post-quantum signatures will be used, or hash-based signatures will be used in the Beam chain.
Awesome. Thank you, Philip. A couple of questions, if I may. Firstly, you mentioned about the Merkle, the values of L and W would also impact the number of private keys that have to be generated per, prover or validated, what you would call. So I'm just curious to understand how this would be implemented. In our current setup, you just generate a single private key and that's used to sign continuously. So how do you foresee this playing out when Beam chain comes live? Do we maintain a Merkle tree of all private keys, and is it generated only once? And which part of the leaf of the Merkle tree is used to sign a given block? I'm just not able to correlate this at the moment.
Yeah, that's a good question. To be honest with you, for the first part of the question, I can also only guess. So the thing is, once you have computed the Merkle tree, so first of all, you need to say, or let me start with the second part of the question. So we know which kind of leaf in the Merkle tree we need to choose for signing a block, because every leaf is assigned to a slot, right? So we start with slot 1, slot 2, and then we know, okay, for slot 1, we need to use leaf number 1. For slot 2, we need to use leaf number 2, and so on. So this is like the slot number tells you which leaf in the tree you have to use. You just enumerate all the tree leaves, and then you go like, okay, we're now in slot 250 or something, and then you pick 250, the leaf. And then the first part of your question is kind of related to this. because you will generate for every slot, you will generate like this, as we saw, this private and public keys. But then the stable, there's like for a certain number of slots, the public key you share with other validators is always stable, right? Because it's the root of the Merkle tree.
Root, yeah.
Yes. So only you need to make sure that you still have the public or the private keys. You only need to manage your, in theory, on your private keys, because you can always recompute the public key and so on. But the thing is, you have to take care of your private keys, but the public key is always stable for at least, I don't know, 500 slots. And then you would regenerate this whole tree, and then you would just share this one root again, which is your public key. So, but the key management, of course, you have to do yourself. And I'm not sure how this will be done eventually. Maybe there's a key derivation function you use, so you just start with one value, and then you can just iterate again and again to generate all the secret keys. This could be done, for example, but this isn't, as far as I know, this isn't discussed in the paper. Does it make sense?
Right. Okay. Thanks. Yeah, I don't have any other questions. Does anybody else have any?
Cool. Yeah, I hope this was helpful. But I think, at least for me, it was it's now a little bit more clear how this will actually, be used in the Beam chain eventually. So at least that's the proposal, as we talked about in the beginning. And I will share the presentation in the Telegram chat afterwards, of course.
Cool. If no other questions, does anybody have anything else that we'd like to discuss? All right. Thanks very much, Philip. Appreciate it. Yeah, really useful stuff. And yeah,
thank you.
We can probably discuss on Telegram what we like to cover in the next session. Cheers.
Sounds
Thank
good.
you, everyone.
Thank you.
Thank you.
Have a nice day. Cheers.
Thank you
Bye.
for joining
Thank
me.
you. Bye.
Thank you.